Hello everyone, welcome to my channel Essentials of Electronics. In today's video, we are going to discuss about one type of digital to analog converter using op-amp. The basics of digital to analog converter we have discussed in our previous video. In today's video, we are going to discuss this specific type of DAC, the binary weighted resistor DAC using specifically IC741. So there are several methods and circuits for producing DAC. However, it is necessary to familiar with all the various circuit schemes because DAC ICs are available which do not require so much of circuit knowledge. Basic efforts are enough to understand the operation of these digital to analog converter circuits. Instead, it is important to know the significant performance characteristic for using the DAC ICs more intelligently. Okay, so I'm going to draw the circuit diagram of a 4-bit DAC converter. So since it is a 4-bit DAC converter, we need to feed in 4 inputs, digital inputs to an op-amp. Let these inputs be fed to the inverting terminal of the op-amp and the other non-inverting terminal be grounded through a resistor in the feedback called RF resistor. Yes, we will start naming it. These are the digital inputs in the form of zeros and ones. Let the values of the resistors be R0, R1, R2, and R3. Yes, and this is the least significant bit, and here we have the most significant bit of the digital input. And V naught, V naught is equal to minus IF into RF. This is the virtual ground. We'll take an example, digital example, and try to convert it into its equivalent analog value. The example is 1, let it be 1001. D0, D1, D2, D3, let it be 1001. For each input data bit of Pn is equal to high voltage, whether usually plus 5 volts, isn't it? So for this will receive a plus 5 volt, 0 volt, 0 volt, and this will receive a plus 5 volt input based on the digital input. The digital input Dn is equal to 1. Or when Vn is equal to 0, then Dn is equal to 0 for n is equal to 0 to 3. These are the basic knowledge needed. So when Vn is Vi for 5 volt, then Dn is equal to 1 or 0 respectively. The value of If is equal to, the value of Is is equal to I sum is equal to I3 plus I2 plus I1 plus I0, where I3 is equal to V3 by R3 plus V2 by R2 plus V1 by R1 plus V0 by R0. This is the value of the Vf. In DAC, for every input bit, the voltage is summed as 0 volt if the bit is logic 0, and the bit is logic 0, then it is 0 volt. If the bit is logic 1, it is 5 volts. Example, if bit D0 is equal to 0, then V0 is equal to 0 volt. If the bit D0 is equal to 1, then the V0 value will be equal to plus 5 volts. Thus, the voltage at the input is either 0 volt. V0 will be either 0 volt or 5 volt based on the digital inputs given. The input resistors R0 to R3 contribute the binary weightages. The current or the voltage contribution from LSB branch to MSB branch is I0 to I3. This is the I0 is the least and I3 is the most. To achieve this, R0 value is 2 times of R1. R1 is equal to 2 R2. R2 is equal to 2 R3. Now, the RLSB has the largest value while RMSB has the least value. 4-bit tag with binary weighted inputs. The operational amplifier here is the summing amplifier and produces an output that is a weighted sum of the input voltages. I sum is the summation of all the currents in the resistors flowing through the feedback resistor RF. So already in the previous slide we have discussed the value of IF. IF is equal to V3 by R3 plus V2 by R2 plus V1 by R1 plus V0 by R0. So we know the output voltage of the operational amplifier is equal to minus IF into RF is equal to minus I sum into RF, which is equal to minus RF into V3 by R3 plus V2 by R2 plus V1 by R1 plus V0 by R0, where V3, V2, V1, V0 is logic 0 or logic 1 for TTL. So for binary weighted currents to flow into R0, R1, R2, R3, R0 is the least significant bit resistor. Therefore, V0 is equal to minus RF into minus RF into 8 times of V3 by R0 plus 4 V2 by R2. We have already given the values of R0, R1, R2 and R3 in the previous slide. So using it in this equation here, R0 plus V0 by R0, which is equal to minus R of divided by R0, taking out a common 8 times of V3 plus 4 V2 plus 2 V1 plus V0. The step size is found by setting data input to 0001 base 2. P step size is equal to minus 5 RF by RLSP. The percentage resolution is 1 divided by percentage resolution is 1 divided by 2 power n minus 1 into 100 percentage. The full scale voltage. So for conversion, all these data are very essential when we understand the operation of the DAC. So we have two methods for this. The first method, V out is equal to minus RF into V3 by R3 plus V2 by R2 plus V1 by R1 plus V0 by R0, where V3 is equal to V2 is equal to V1 is equal to V0 is equal to plus 5 volts. The second method, For finding out the full scale value, set input for triple for 111 binary is 15 base 10. It's equivalent decimal I have written here. The full scale value is minus 5 RF by R naught, which is equal to 1 base is equal to minus 15 into 5 RF by or not. So which is equal to the step size into maximum digital input value, or also it is equal to step size into 2 power n minus 1, where n is the number of bits. So this is the way we need to calculate the output voltage of the tag. So in today's video we have discussed the output voltage calculation, full scale value, its resolution, calculation values for binary weighted resistor DAC. Thank you.